You ever had an app just crash on you or a website completely glitch out? Of course you have. It happens to all of us. Software, well, it's famous for being buggy. But what if it didn't have to be? What if we could actually build code that was mathematically, provably perfect? Today, we're diving deep into that incredible quest for flawless software. And that right there is the big question. It's an idea that has driven some of the sharpest minds in computer science for more than 50 years. And it's a pretty radical one, right? The idea that we could treat a computer program not as some piece of engineering that you just test and hope for the best, but as a mathematical theorem that you can actually prove. Now, to really get why that idea is so revolutionary, you gotta understand what programming used to be like. For the longest time, it really wasn't a science. It was more of an art form. An intuitive, but let's be honest, a deeply error-prone craft. I mean, programmers were basically working from gut feelings and experience, but the results were often totally unpredictable and just riddled with bugs. And as software started running everything, I mean, banks, power plants, you name it, this craft approach just wasn't going to cut it anymore. We needed something way more rigorous. And then things started to change, right around the late 1960s. This is where the story takes a really sharp turn. And it's all thanks to a brilliant computer scientist named C.A.R. Hoare. He came along and proposed this completely radical new way of thinking about code. Okay, so what Hoare is saying here is huge. It's this core idea. If programs are really just math, then we can use the tools of math, logic, proofs, to make sure that they're correct. Hoare's whole vision was to lift programming up from the shaky craft into a real engineering discipline, one built on the solid bedrock of mathematical proof. But look, a vision is one thing. To make it real, you need tools. So Hoare went and developed a formal system to turn his big idea into a practical, hands-on method for actually verifying code. He called it Hoare logic. And the idea is actually simple but incredibly powerful. If code is math, then it's got to have rules, right? Just like algebra or geometry, Hoare logic gives you those rules. It lets you analyze a program line by line and prove with absolute mathematical certainty that it does what you say it's going to do. And at the heart of the system is something called the Hoare triple. The best way to think about it is like a contract for every little piece of your code. First, you have the precondition, that's P. It's what must be true before the code runs. Then you have the command, C, which is just the code itself. And finally, the postcondition, Q, which is what you guarantee will be true after the code is done. If you can prove that starting with P and running C always gets you to Q, then congratulations, that piece of code is correct. Okay. So proving a single list of instructions is one thing, I get it. But our phones, our computers, the entire internet, they're all doing millions of things at the exact same time. How on earth do you prove that a system that complex is correct? And that's really the heart of the challenge, isn't it? A traditional program is like a simple recipe. You just follow a single list of steps, one after the other. But a modern system, that's more like a chaotic kitchen with a dozen chefs all working at once, sharing ingredients, shouting at each other, trying not to mess everything up. So Hoare tackled this too, with a model he called Communicating Sequential Processes, or CSP. Think of it as the official rulebook for that chaotic kitchen. It gives you a mathematical way to describe how all those chefs talk to each other and coordinate, making sure that even with all that chaos, the final meal comes out absolutely perfect, every single time. So now we've got these incredibly powerful tools, Hoare logic and CSP, and with those in hand, a real movement started to form. The goal was to take these ideas out of the ivory tower and into the real world to build ultra-reliable software. And this whole effort really came together as the Verified Software Initiative. This wasn't some small thing. This was a massive global project. With Hoare as a kind of guiding light, top research groups from all over the world came together with one single mission: to build a new generation of tools that could construct provably perfect software. And their guiding principle was something called correctness by construction. Now, the key here is this isn't about writing code and then trying to test all the bugs out later. No, this is about building correctness in from the very, very beginning. You start with a mathematical spec, and you make sure every single step along the way is provably correct, right down to the final line of code. But the million-dollar question is, does all this theory actually work in practice? To find out, they set up a landmark experiment, a project designed to be the ultimate real-world test for these super rigorous methods. So, let me introduce you to the tokeneer system. The goal was to build an ultra-high security access system, basically a digital gatekeeper for a military installation. Talk about a trial by fire. For a system like this, mostly correct is a total failure. A single bug isn't just a glitch, it's a potentially catastrophic security breach. So, to build it, the team used a very specific set of tools. For the initial design, they didn't just write a document. They used something called Z notation to define the system's requirements with pure mathematical logic. Then, for the actual code, they used a special programming language called Spark, which is designed from the ground up to be verifiable. And the whole time, they were guided by that one core principle: correctness by construction. And the result? It was a massive success. The system was incredibly robust. But you know what? Maybe the most powerful takeaway was a human one. They found that using these formal methods forced the developers to think with this intense precision and clarity that just eliminated confusion before they even wrote a single line of code. So if this works so well, why isn't all our software built this way? Well, the biggest roadblocks are really cultural. There's a steep learning curve, for sure. And frankly, there's a pretty widespread fear of mathematics in the programming world. It's just a very, very different way of working.
But here's the thing. Even if not every programmer is sitting around writing formal proofs, Hoare's axiomatic approach, this whole idea of building systems on a foundation of logical rules, it has left a profound and lasting legacy.
This way of thinking is now foundational in fields that go way beyond its origins. Its influence has spread into some of the most advanced techs that we use every single day. I mean, yeah, of course it's key to verifiable software, but its ideas pop up in really surprising places. The same logic that makes a program correct can help design the recommender systems that decide what you see online. But maybe its most critical job today is in the quest for safe and reliable AI. How do you prove an AI won't cause harm? Well, you need a system of logic, a set of mathematical guarantees. And that's a direct legacy of Hoare's work. And that brings us right back to where we started. In a world that runs on code, in our cars, our hospitals, our banks, we now know that perfectly reliable isn't just some fantasy. The tools actually exist. So the final question is for us. For the software that our lives truly depend on, should we really demand anything less than proof?